Indiana University East Department of Science, Common Ion Effect and Buffers. So, what we want to do now is to look at what happens with the acid ionization of acetic acid. And you probably know by now that this is the reaction that occurs. You have CH3COOH, acetic acid, undergoing ionization, and this is a weak acid, so this is an equilibrium. And so you get H plus and the conjugate base. And the common ion idea is that you are looking at two things on both sides of the equation with a common ion. So what happens when I add some to a solution of the weak acid, some of its conjugate base? This shifts the equilibrium backwards because I'm adding in the conjugate base, so that's the common ion. Therefore the equilibrium is shifted to the left, and this effect, shifting the equilibrium to the left, thus causing the pH to be altered, is referred to as the common ion effect. So a buffer solution is formed when you have a weak acid. It has to be a weak acid, not a strong acid, because you need that equilibrium to go both ways, and its conjugate base. So here acetic acid and sodium acetate, and there has to be appreciable amounts of both for it to work. And the ratio of base to acid they have to be similar in concentration. Typically we say that it will work if the ratio between the concentration of base to the concentration of acid is between 0.1 and 10. And this is how you form a buffer. Note that in practical terms, when you make one, a lot of times what people do is to take either a weak acid or weak base and then add strong acid or base to neutralize it, forming the conjugate acid or base needed. And when you have a buffer solution, let's see. What happens with a buffer solution is that when you add small amounts of strong acid or base, say here we're adding HCl. If you look at just water, you can see that the pH changes appreciably as HCl is added, pretty quickly too. On the other hand, for a buffer solution, it resists the change in pH when small amounts of strong acid or base is added, and therefore it is a buffer against pH changes. So how do buffer solutions resist changes in pH? Let's consider an equimolar mixture of acetic acid and acetate. So I've got the two here, and this is the acid ionization. So what happens if I add some strong acid to a mixture? Well, since I got both of these and I'm adding H3O plus here, I'm going to add some more product that drives it towards the reactant site. So I have more CH3COOH, which is not H plus, and I lose some CH3CO minus. But the key is that the concentration of H3O plus has gone down as well. As a result of that, essentially you lose your H plus. So this leads to a smaller increase overall in the H plus concentration than if there wasn't a buffer mixture here, and therefore this resists changes in pH, which, as I may remind you, is the concentration of H3O plus at equilibrium. When OH minus is added, hydroxide is added, so a base, then we can look at what happens in the base ionization of the acetate ion, so the weak base. The OH minus is going to react when it's added to a system at equilibrium with the weak acid, and it reacts, I add OH minus, driving the equilibrium towards the left, and thus neutralizing some of this OH minus. By neutralizing the OH minus, I'm essentially removing it from affecting the pH per se, and therefore the pH change in the buffer solution is much less than otherwise expected.